untrained. So that never happened. What never happened? Exactly. Okay. Relational databases are designed towards ensuring that any queries receive correct and current data, right? So if you ask the database a question, it gives you the right answer. And this is implemented through 4 properties with the letters ACID, thus known as ACID properties. So, atomicity, consistency, isolation, and durability. And mention right off the bat, this atomicity here is a little different from the one we talked about earlier with database fields. So, hypothetical example. You are updating your Facebook relationship status from whatever it is to it's complicated, okay? Because that's a thing. Now, atomicity, first one. The principle of atomicity says if you have a set of related database actions, they're atomic. Either they all happen or none do. For example, within the database system itself, if you update your status, you also have to update any copies of that status that exist as backups, right? So Facebook typically has multiple copies of anything, so if you update your status, boom, you have to echo that to all the existing backups. And if any of those updates fail, the entire action fails, your status is not updated. And that prevents the possibility of having multiple copies that are supposed to be the same thing having different values. Does that make sense? Questions? That's atomicity. If you have a set of related database actions that basically one action is going to force changes to others, they all have to happen or none of them do. Okay. Second one, consistency. Consistency says actions are processed in sequence and according to the rules of the database, which is kind of a fancy way for saying the database works the way it's supposed to, is what it boils down to. But here's a concrete example. Suppose you unfriend somebody prior to announcing your status change. Well, if you've unfriended someone first, then all the consequences of unfriending that person should happen before the status change gets implemented. Which means the unfriending happens first, and your former friend will not receive the announcement of your relationship change, right? Because it's no longer visible to him. Another way of describing this, any database operation starts and ends with a consistent database. So, if you unfriend someone, when you unfriend them, they can see all of the stuff that they're supposed to see. Once they've been unfriended, they can't see the stuff, right? Because they're not your friend anymore, anything that's non-public. Okay, so basically, consistency just means whatever database rules you have in place, they have to be followed, and any operations to that database have to happen sequentially so that you don't run the problem, right? The possibility could happen that, for example, we have 2 things. One of them is unfriend. I gotta use a smaller font. When Paint decides it wants to respond, because Paint isn't in a hurry. What does Paint give a fuck about? Paint doesn't have shit going on. Okay. Unfriend and status change. Okay. So it should happen, right? You unfriend the person, and then you launch the status change. What you don't want to happen is have this unfriend operation still be hanging when the status change is complete. Right? Because if that happens, then there'll be nothing that says, oh, this person is still your friend. They haven't been formally unfriended yet. You've initiated the process, but it hasn't completed, and therefore your former friend would be able to see that. Okay? That's the problem. That's an example of a consistency violation. So things have to happen sequentially. You unfriend first, thus they are unfriended by the time the status change happens. And so when the unfriending is complete, likewise, they do not see the status change. Okay? Consistent. A non-friend does not see the later status change. Okay, so that makes sense? That's consistency. Well, that's an example of consistency anyway. Okay. Next one. Next 2. Isolation and durability. So, isolation means no database operations affect each other directly. So each happens the same regardless of anything else going on in the database. What this means in practice, operations on the same data don't interleave. Okay, so it's a little bit difficult to describe this one, but the best way I have come across, what seems to work for me, is explaining it with an ATM. So, suppose I have a bank account, and I'm at one ATM, and my wife is at another ATM. And we're both logging into the same account. Me, my wife. Okay? We're at different ATMs. Now, initially, we both read the balance. And because I'm living the prof life, let's say I have $1,000 in my bank account, because that's lots of money. Okay. Likewise, she reads the balance at the same time, and since nobody's done anything yet other than read the balance, we both see the same value, $1,000, right? Okay. Well, in isolation, suppose we both want to withdraw money, and suppose our max withdrawal amount for the day is $600. Well, I launch an operation, withdraw $600, and what should happen before anything else happens in the system, new balance goes down to $400, right? That's what should happen. But suppose at the precise instant I initiate my withdrawal, my wife does exactly the same thing. Okay? She also withdraws $600 from the account. Okay. In a well-designed account, what should happen is something in the system should notice, oh, these two users are attempting to access the same data. We have to put a lock on one or the other until the first operation is done. So whichever one of these withdrawal operations initiates first, the fact that it's being initiated should say, okay, nobody does anything to this system until this thing is done. Okay? That's the way it should happen. Which means, right, then likewise, whichever one of us finishes first, we'll get this. And I'll make a note here. With isolation, one but not both can complete the withdrawal. Okay? Because there's not enough money for both of us to withdraw $600. Now, if these aren't isolated, right, so you need to understand a little bit about the way a database works. The way a database works is not that the computations actually happen inside the database. What happens is you read a value from the database, the application does some kind of change to it, resulting in a new value, and then that new value gets written back to the database. Okay, so in this case, if I try to withdraw 600, essentially, app will calc a new balance, 400, and write it to the database. Okay, and that's the same thing that's going to happen over here. Okay, calc new balance and write 400 to database. In both cases, the same thing's going to happen if they're not isolated. So that's what they're going to try to do. If they're not isolated, they're each going to try to do that, and then what can happen, they both actually withdraw the $600, and then whichever one of those is the last one to complete writes the new balance of 400 to the system. Right? And then at some point the banking system figures out, oh shit, you took out 1,200, but we only marked it down to 600, and they come after you to get it back. But it's a big hassle. Okay? That's what happens if you don't have isolation. Now, this seems like a stupid thing, right? This seems like something the banking system would have figured out decades ago, right? And yeah, actually, it is. However, you guys ever heard of Bitcoin? Yes. Yeah? You guys ever heard of the Poloniex exchange? Well, let me give you an example. So the guys that were doing the Bitcoin stuff, they were computer guys, probably math guys, possibly organized crime guys, but they weren't really network and database guys. And so they had this. There's a Poloniex exchange hack. This one, boom, loses 12.3% of its bitcoins in Bitcoin exchange hack, around the order of $20 million. This is this is like 5 years ago. But the idea is this. So if you look at this, and I have this same article linked to in a subsequent lecture, so it'll be there. Hacker discovered that if you place several withdrawals all at practically the same instant, they get processed at about the same time. This results in a negative balance, but valid insertions into the database. So basically, they don't catch up with the fact that people withdrew multiple times in such a short interval. Okay? They planned their system around milliseconds. The hackers figured out a way to do it in microseconds and basically flood a bunch of transactions under the rug before the system figured out what was going on. So, not all databases are well designed, is the takeaway from this. Okay. But had they done that, they would have saved themselves that $20 million and all the other negative consequences thereof. Okay, so that's what we mean by saying operations on the same data don't interleave. If I want to withdraw $600, I do that in sort of a bubble, and nothing else can touch that balance amount until that single operation is completed. It's isolated from other database operations. Yes?
So does Facebook also need to do that for any activity?
Generally, isolation is very important for transactions, especially for big transactions, right? Like you might let it go if it's, people spending $1 and you're like, what's the worst that's going to happen? Hackers aren't really going to chase those kind of crumbs. But if it's multi-million-dollar bank transfers or Bitcoin withdrawals, you really have to pay close attention to that. So transaction systems, that's someplace where you really want to follow ACID properties, and so you have to set up your database often on like a big mainframe type machine that can handle that many more or less simultaneous operations. You see the eyes kind of go in there. But some stuff that Facebook does is really important to keep this kind of consistency. Some things that it does aren't. For example, the people that are looking at a particular photo and liking it, right? It'll eventually catch up, but in the space of like 5 or 10 seconds, if one data center has a slightly different copy of who liked a picture than another does, who cares, right? Yeah, it doesn't really matter. It's not like a $20 million Bitcoin hack. So Facebook does keep strong consistency guarantees in a few places, again, primarily transactions, but a lot of other stuff, it's found ways to cut corners and make it work faster. Okay. Last one, durability. Durability just means if something goes wrong with the database, you can recover, right? It says robust against failures. That means if something goes wrong in the system, for example, one backup copy shits itself, you still have 2 others. One server goes down, you have a bunch of others that can take up the load, things like that. If the system fails after your status change has been processed, then when the system recovers, your recent status change won't be lost. That's an example of durability, right? Something changes once a change has been formally made to the database because of atomicity, right? If you make the change in one place, it happens to all the backups as well. That way, if the system, that particular machine, the first one you wrote to goes down, that's okay. You still have the 2 backups that show the correct current state, okay? And I suppose it's theoretically possible you could have multiple machines go down virtually simultaneously. Once in a blue moon, you'll have like a data center that gets hit by a bunch of bolts of lightning all about the same time, and they can actually permanently lose a little bit of data when that happens, but it's pretty rare. It's like, a once a year kind of thing, and it's like a couple people lose images. So, all right, other questions about these? These are the big 4. Okay, atomicity, consistency, isolation, durability. Got to know what they are. All right. Next thing. As you might guess, or if you've been paying attention, you've heard me say it, strictly following these ACID properties inhibits performance. It makes your database run slow, especially when it's big or busy. So, for example, if you have a big system and certain lumps of data are popular, users might have to wait a long time on operations. For example, suppose you adhere to strict ACID properties for people making comments, right? People want to make comments below an image or below a post. In an ACID system, you'd have to say, this person is starting to create a comment. Once that process is launched, you have to wait until that comment is done before the next person can add a comment below it. That'll slow things down a lot. Other stuff, a very simple one that can often happen. Imagine if you have a very large table. And you have, what else? You have another very large table. Now, what's going on with these large tables? Well, two operations, two ops. Number one, some user wants to query the whole table, but not on a standard index. Okay? One of the things we'll eventually talk about in this course is how indexing is important to basically be able to quickly sort through data to find what you're looking for. If the user is running a query that's not sorted on a standard index and these tables are very large, it can take a long time to run that query. While that query is running, though, no writes are possible because of ACID, right? If you're going with this basic relational database model, you say, well, somebody's running a query. You want to change anything in the query? Nope. You got to wait until this one whole big operation is done. So if you have a query that, one of the ones I said, it could take like a week to get done or something, it kind of locks up your database for the whole week, right? And nobody can do anything to it. There are ways that you can kind of get around this by restructuring your data in different forms. But the bottom line is if you have a very big database and you're trying to run an operation that takes a while to get done, nobody else is going to be able to access those records to change anything there until that whole big operation is done. Other people might be able to read from it, but nobody's going to be able to write to it. And if you're running transactions, that's going to slow transactions down because the system won't be able to give you a confirmation that the transaction went through until after that query went through. Okay? So ACID properties are nice in the sense that they ensure your database gives the correct answers, but at scale, you have to find workarounds in some way. Okay? And the workarounds can basically be either allowing some degree of inconsistency for trivial things, or what other places do is they group the data into separate chunks so that then the chunks are relatively isolated from each other, and you don't run into this problem. Okay. Is that adequate? I mean, I know it's a little abstract, but yeah, it's good?
It's like a printer query.
Sure.
If a job gets stuck, it runs out of paper, you can't print
Yeah,
anything else.
you got to have that resolved before the next thing goes through. Yeah, you can't print two documents at the same time. Yeah. Okay, yes. Well, I'm saying if Facebook maintained those comments in an ACID database type structure, yeah, they'd say, oh, I see we've created this entry for you, right? You have to fill that out before I do something because all of those comments are going to be associated with that post. And so it'd be like somebody is doing something with this post, so it's going to be locked until you're done. Okay? And this is an example. Facebook doesn't actually do that, right? If you've paid attention to Facebook, even though somebody else is typing a comment above you, you can still enter in a comment below. Because Facebook doesn't do that, because that's one of the corners Facebook can cut. Okay? It doesn't matter too much if, somebody's taken half an hour to, plot out this carefully thought out comment. I'm just going to write down below it, haha, real fucking funny, right? And I'm done. Okay? I don't need to wait. Yes? Yes. I can. Let's see if I have an image that goes with it. Okay. So with consistency, the idea is simply you follow the rules of the database, which tends to demand that things that are related, data that could potentially interlap with each other, interleave, happen sequentially. So what we would want to do in the case that I have in the slides, if you unfriend someone, you want that unfriend to be operation to be complete before you say do a status change that then that unfriend person wouldn't be able to see. Yeah? So in the initial stage, right, if nothing happens here on the left, if I just do my status change and that goes through and that person is still my friend, it's consistent. He's a friend, he can see my post. But if I unfriend this person and I do the status change, it would be an inconsistency for this unfriend person to see my post. Yeah. Okay. All right. So yeah, two problems that can happen. Deadlock and live lock. So I believe we covered deadlock in a little bit. Maybe we don't. All right, well, I'll talk about deadlock right away. So, deadlock is the case where two operations actually block each other. Okay, and I have an example there. Two people trying to post on each other's profiles. In Facebook, when somebody posts on someone's profile, not only does it create that post, but it also creates an activity log entry. But if the other person is doing the same thing at the same time, and the system is strictly following ACID, they're both going to be waiting for the other one to finish before they can update each other. But I'll give you perhaps a clearer example. Suppose, once again, a table. It doesn't have to be very large. Okay? I don't know how the font dropped like that. Okay? So we have a table. And let's say there are two rows that we're interested in querying. There's going to be row X and row Y, and we're going to do an update on each of them. X and Y. We're not actually doing a query, we're doing an insert. Okay. So, our first operation, op1, change X, then change Y. Okay? But our second operation says change Y, then change X. Well, what's going to happen, again, if you're strictly following ACID, the first operation is going to try to change X, and at the exact same instant, the second operation is going to try to change Y. And there's no problem with that, because both of those aren't in use at the moment. But the second operation, right, when operation 1 tries to change Y, he's going to see, oh, there's a pending operation, right? Y has been changed, but there's this thing also going on. Because remember the principle of atomicity? If they're all related, you wait for them to go together as a group. So this guy is going to be in the same boat. He's going to say, well, I changed Y, and I want to do something to X, but X is locked until operation 1 is finished. And they're both just going to be sitting there staring at each other waiting. Hey, how come you're not done yet? Well, how come you're not done yet? Well, I don't know. They're deadlocked, okay? And the system shuts down. Now, if a system is big, this sort of thing can happen surprisingly often. It's pretty common to have two operations attempting to access, overlapping sets of data. And it's a problem, because then your database hangs up for a while until finally the operation attempt, aborts. So it says, oh, you timed out, didn't work, try again later. But if they both try again later at the same instant, guess what's going to happen? Yeah, so that's the sort of problem that can happen. On top of normal performance issues, you can actually have things just grind to a halt sometimes too. Now again, there are ways around that, but they add more overhead to every operation because you have to check then if any operations are overlapping, which slows down your system even more. So, operating at scale with ACID is often a problem. So, Facebook, to deal with that, has in many cases chosen a policy of what's called eventual consistency. The database might not be absolutely consistent for everything all the time, particularly in the case of separate data centers. But eventually, yeah, it'll all work out. Eventually, it'll catch up. But it's not going to try to do every operation in real time necessarily, and it's not going to always make sure that one resource is available or needs to be changed before it does anything with another one. So, what can actually happen? Different users might occasionally, for a little while, see different information. And the good example is, you post a picture, if it's at two different data centers because you have friends around the world, well, your friends connected to one data center might see a different set of likes in the short term than the people looking at it at the other data center. But it'll even out, probably 5 or 10 seconds down the road. It'll be okay. But yeah, there'll be that little bit of inconsistency. But it's not like they're going to get on the phone and call each other and say, hey, I just saw this picture and it has 12 likes. And they're like, oh shit, I saw it and it has 13. We got to call Facebook. Right? They'll be like, okay, people like it. Fine. Move on. It's an inconsistency, but it's a trivial inconsistency that doesn't actually hurt anybody. So Facebook says, you know what? We're going to prioritize speed over perfect consistency. Okay? All right. So that's the technical details. We got a few more slides. We'll talk about some NoSQL systems. So the first basic one is what's called a key value store. So Facebook, like I said, uses a different database model, prioritizes speed over perfect accuracy, eventual consistency. One of these cases is something called NoSQL. NoSQL has certain design goals. Number one, wants to be flexible, so it's easy to add or remove data fields. In a relational database, like I said, because you want that offsetting capability to know that, oh, if I start at such and such a record, all these fields are at the same size so I can find what I'm looking for. Relational database, you can carefully calibrate like that, but because of that careful calibration, it's really difficult. It's a pain in the ass to add or remove data fields. NoSQL, it says, you know what, we're not going to rely on that. So in some cases, it's going to be slower. Some things that relational databases are good at, but we're going to allow people to do that without causing a lot of headaches. And part of the thing with these NoSQL databases is you're generally not running queries across multiple tables, and that's where this advantage comes in. Other things, accommodating different data sizes or structures. Remember, with a relational database, if you want to fit everything to the same size, if you say, well, the biggest size that this image can be is 10 megs, so I'm going to have to allow 10 megs for that field, even if most images are way smaller. Key value store says, you know what, we're going to try to use our data space efficiently because that's a trade-off that we're going to make. If Facebook actually has actual exabytes of data, if they're not using their data space efficiently, they could be talking about actually requiring zettabytes of space, like 1,000 times more space than they actually are using, and they'd have to pay for all that. That would be horrible. Last one, auto sharding. So auto sharding basically means if your lists get so big that they have to be split up across different devices, it can automatically do that, and you don't have to go through a whole careful calibration process like you would with a relational database. So, short version is, NoSQL is designed for flexibility versus the ability to run queries across tables. That's the big trade-off. Okay, and if you want, I have Mongo, which is one of these NoSQL systems for document storage. Talk just a little bit in there. Okay. So Facebook has designed a whole bunch of NoSQL systems over the years. Haystack we talked about. You may have heard of Cassandra. I think I mentioned that on a slide a little bit back. Memcache, that's one of those in-memory systems that's RAM for popular stuff, hard drives for less popular stuff. Scribe for system logs, some others. They've done a whole bunch. Facebook also uses a SQL-based MySQL platform for managing wall posts. And the reason is, wall posts have a pretty standard format, right? There's a max length. If somebody links a picture in it, well, you don't actually have to store the picture in this database. All you have to do is a field pointing to where the picture is stored. So wall posts can be managed in a pretty standard format, which is not true for many other data types. But because it can, then yeah, they go ahead and use a relational database for that. Okay. By the way, you don't have to know what any of these are. Like, I'm not going Haystack, you have to know what that is. But just be aware, yeah, Facebook runs a lot of different NoSQL systems for different uses, right? It's not that they have one giant, massive NoSQL system that serves all their needs. Just like businesses have many systems for particular uses, they set up particular NoSQL database systems for particular uses. Okay. So, this one, key value database. So the basic idea with a key value database is this. Also sometimes called a key value store. So remember, in a relational database, we had something called a key or a primary key that uniquely identifies records within a table. We still have that. Key is still the key for unique ID. Okay? Value can be any data structure. Absolutely anything. I mean, yeah, you have some upper bound space limit, like maybe 5 terabytes or something. But as long as you manage that, yeah, any data structure. So, this is a neat thing. So your record essentially, right, your table will essentially consist of keys and values. Good. And this is tremendously flexible. Because why? Because inherently, I don't impose any structure on the value. So if I want to change something inside a value, yeah, fine, go for it. You can do that. It's easy. Okay? The downside, so let's make a list of brief things. Number one, good things. Efficient use of space, of data storage space. Okay? Because I don't need to have a standard size box for a field, regardless of whether that box is full or not. The value is just going to fill up what it needs to. Okay? And what else? Custom data structures, easily changed, can be entirely different within a table. So whatever I'm storing here, for example, I could store it as some kind of object descriptor, use some kind of object description language to say, there's this thing in here, it has fields. In a sense, you could actually have each value be a separate table if you wanted. And this is useful because you might have different objects following different formats. Okay? So that's the nice thing. It's efficient, uses space efficiently, and it's flexible. So if Facebook at some point down the road says, you know, we want to store some extra different kinds of data, they don't have to totally re-engineer their database to do that. Bad things, okay? I'll say, for all practical purposes, okay, no cross-table queries. You could do them, it would just take a really long time. The other problem is searching for particular fields within a table can take much longer because you have to find them and you're not even sure they exist for all records. Okay? In a key value store, you cannot take for granted that any particular field exists unless you've made that an overriding fact for the particular setup you've made. In general, right, in a relational database table, if you have a list of customers and there's a field last name and a field first name, you know every customer has a last name and a first name because the database is set up that way. You just go scan through. Here, right, number one, these values can be big, so you actually have to scan through all that potentially very large value data looking for those particular fields if they're even there, which means you have to scan through the whole value record, okay? Second, you don't even know they're all there, right? So if you have them grouped together randomly, yeah, you got to search from one end to the other. It's kind of slow for that. Okay, so good things. This is nice. Key value table is very nice if what? Is very nice if all you're doing is retrieving data in some never changing format. And a great example of that is images, right? You upload a photo to Facebook, it stays there. Facebook has exabytes of photo data. They want to use their storage space efficiently. They know nobody's ever going to go in and edit a photo because they basically don't have that capability. There's no really good reason to do cross-table queries with photos because you just want to look up a particular photo from a particular user. So each value in this key value table could just be a particular photo album, and that would be easy to find. Okay? Does that make sense? Yeah. Okay. So again, like so many things in life, the right tool for the right job. Key value stores aren't going to solve every problem in databases, but for this problem of storing a whole lot of images of potentially wildly divergent sizes, these are great. Okay. All right. So very flexible, very scalable, pretty fast for the right job, right? Problems, you can't do query limits that involve table joins. Table joins is like combining data from a cross table. I mean, you could do it, it's just really slow. Okay. So, where do key value pairs make the most sense? Well, number one, objects with indeterminate form. like a web page, right? It would be a very bad idea to store a complete web page in a relational database because you'd have to come up with a column for every field you want to store, and there's no inherent structure for a web page. Also, things like Facebook user history, right? Some users are brand new, have nothing. Some users have a very long history, very active. You need to have a separate column for the most things that any user could have ever possibly done for as long as that user is going to exist, right? Would not be a practical way to design a relational database with that kind of open-ended set of fields. And like we said, very large objects needing horizontal database scale. And that just means you have to add on more machines, okay? One of the problems is if you have a lot of data, if you can store all your data on one machine in memory, especially if you can store it all in RAM, you can process queries on that table very quickly because it's all happening at electronic speed. But when you have very big piles of data running on separate hard drives, and you try to do those kind of cross-table queries, a lot of stuff starts happening at mechanical speed, which is really going to slow everything down. So, for very large objects or tables involving very large objects that are likely to spill over into many machines, relational databases, basic ones aren't going to work very well. You can do some tweaks, Google does it, but yeah, for a lot of cases it's going to be difficult. Last thing is if you have combinations of unrelated data used together. So, for example, if you have some security application that uses these long log files, it could be like gigs of data of how people have been interacting with the application. All that kind of stuff mixed together. Again, there's not going to be one standard format. So what you do, if you have a batch of stuff that you want to analyze for security purposes, you bundle all that together into a value and store that in your database to be retrieved later. Okay? You don't want to come up with a separate table for every unique combination of this kind of data. Instead, you just have one big value. Okay. Almost done. Hang in there. I know it's Friday and everybody exits and stuff. Last thing. So market status. You don't hear a whole lot about NoSQL databases in college, I suppose. Like even 510 or 410, the database course here, barely mentions them. I teach 520, which is a follow-up from that. And I always ask if they've heard about it. They say, well, they tell us that they exist. Okay. Reason is, a lot of the money, as far as people track it, is still in relational databases. So those green bars there, that's all the money that goes into relational databases. The other colors at the top, the black and the blue, that's different kinds of NoSQL databases or other